Hi, this is John Whitaker for the Probability 1 graduate level class. And this is our 8th video lecture. Hello, Wayne. Hello, Travis. And today we're going to be looking at some more continuous random variables. We're going to get one more fact having to do with the uniformly distributed random variable. We're going to look at an exponential random variable. And we're also going to look at the gamma random variable. And we might even mention the normally distributed random variable during this video lecture. We have had our first on-campus meeting, and at that meeting, Travis asked me about what things, in terms of background material, he could be studying, and I talked about integration, in particular with two variables, so a double integral. But that isn't the only, that isn't the only background material. So there's more integration that can be involved, and I might have mentioned that, but today we're going to rely heavily on integration by parts, and we're going to be talking about improper integrals as well. So I'll mention those as we're doing our work here. But the first thing I want to do is recall the definition for a uniformly distributed random variable. A continuous random variable X, so these are some calls, is said to be uniformly distributed. If the PDF of X is f of X is equal to, it's 1 over b minus a if X is an element from A to B, and it's equal to 0 otherwise. So we talked about what the expected value was of a uniformly distributed random variable. We talked about what the variance was last time. And so what we want to do here is we want to talk about the CDF. So this is the second thing that we're calling. Recall the CDF of X is big F of X, which is defined by the probability that X is less than or equal to A. Okay. This A here and this A here are not necessarily related in terms of the symbolism of the definitions. Okay? What we want to do is we want to find the CDF of a uniformly distributed random variable. So here, let me write this down. We will find the CDF of a uniformly distributed random variable. With parameters I'll say with parameters A and B that tell me where the PDF is not 0. So here, the CDF will be denoted instead of X, I'm going to use the variable little t. Okay. So the thing that I realize is that if we consider a t less than the a, less than, then the probability that x is less than or equal to A, well, I'll say less than or equal to T. Okay, well, that would be the integral from minus infinity to T, put this in proper angle, of f of x dx, where x is the PDF of big X. But when t is less than a, this PDF is defined to be 0. And that's just 0. That's the first thing we noticed. Now, if we consider other t's, let's say, for instance, if t is bigger than a, yet less than b, then the probability that our uniformly distributed random variable is less than or equal to t. Well, again, by the definition or what the PDF does for us, this answer is the integral from minus infinity to t of f of x dx which is equal to, here, from 0, from minus infinity up to a, this is 0. And so we might as well start from a up to t. Here, what the f of x would be in this case, the non-zero part, is 1 over b minus a dx. I should write down something here. This is really f of t, okay? So here, this integral is 1 over b minus a, the antiderivative, would be 1 over b minus a times x. We evaluate from a to t. And when I do that, we get t over b minus a minus a over b minus a, using the fundamental theorem of calculus. So that's t minus a over b minus a. Now, if t is bigger than or equal to b, then f of t, which is equal to the probability that x is less than or equal to t, is equal to an integral from minus infinity to t of f of x dx. But that's equal to is the integral, well, remember f of x is 0 logical spots, so it's the integral from a to b in this case, of f of x dx, and that ends up being the integral from a to b of 1 over b minus a dx, which is equal to, using the fundamental theorem of calculus, 1 over b minus a times x, evaluate from a to b, so that's b minus a over b minus a, which is equal to 1. So I'll summarize what we found. Thus, so you figure this is back. If x is uniformly distributed, with, I'll say, parameters a and b, then the CDF of x, and I'll write down big F of t, is big F of t is equal to the this is what we found, 0, if t is less than a. It was t, whoops, it was t minus a over b minus a if a is less than or equal to t, which is less than b, and it was 1 if t was greater than or equal to b. So that's what we found. Excuse me. The next thing that I want to turn to is the definition of the new continuous random variable for us. That is a continuous random variable name x is said to be an exponential random variable with parameter lambda and that's what we have if the PDL of x is f of x is equal to lambda times e to the minus lambda x if x is greater than 0 and 0 otherwise. Where lambda is greater than 0. So the first thing we want to do is we want to show that if we integrate this, we're going to get, if we integrate this PDF, we're going to get 1. We integrate over the whole real line. So here, note the integral from minus infinity to infinity of f of x dx is equal to, well, a lot of times this function that we're integrating is 0. So when we integrate over the region for which this function is 0, we just get 0. So we can rewrite this as the integral over the non-zero region for f of x, which is 0 to infinity. And what f of x is lambda times e to the minus lambda x dx. Here, this is equal to improper integral, so I'm going to rewrite this as limit as a dummy variable, t goes to infinity, of 0 to t, lambda e to the minus lambda x dx. And the way that we can integrate this is through u substitution, so I'll take my time here. What we'll do is we'll let u equal to lambda x and du, or we can let it be minus lambda x. Du would be equal to minus lambda dx. And so what we get is this is equal to the limit as t goes to infinity of this will be from 0 still to infinity, because when u is equal to minus lambda x, when x was 0, we still got out 0 for the form and this should be t. Well, here, when I'll just write down t here and we'll make the substitution back. So what I'll get here is the I need a minus lambda, so I'll rewrite the problem. This is e to the minus lambda x minus lambda dx. I needed that minus lambda for the du. I have to put a minus out front to compensate for this minus here. And this is equal to the limit as t goes to infinity of minus the integral from 0 to t. I'm going to indicate that these values are for x. So x going from 0 to x going to t. Here this will be e to the u, and then minus lambda dx is du. And that's an antiderivative that's easy to get. So this is the limit as t goes to infinity of minus e to the u to be evaluated from x is 0 and up to x to be equal to t. So I'm being very formal here. We resubstitute in for u what it's equal to. So this is the limit as t goes to infinity of minus, then e, and then u was minus lambda x. And I need to evaluate that as x going from 0 to t. So doing that evaluation, this limit as t goes to infinity of minus e to the minus lambda t minus a minus makes a plus e to the 0. Now, when we let t get really, really big, remember lambda is positive. That's why we need lambda to be positive right now. Lambda is positive, so lambda times something really, really big is a huge positive number. And you put that to make that negative, you got e to a really big in magnitude negative number. That is that number as the power gets more and more negative, bigger in magnitude, goes towards 0. So this is equal to 0 plus e to the 0 is 1, and we just get 1. And so that's what I wanted to show. As a fact, if x is an exponential function, or exponential, random variable, with parameter lambda, then the expected value of x is 1 over lambda. Let's prove that. Now, this proof, I think, is going to involve integration by parts. Proof. Put all of that x be exponential with parameter lambda greater than 0. Then the expected value of x by definition is equal to the integral from minus infinity to infinity of x times f of x dx, where f of x is the PDF. But the PDF is 0 a lot of the time. So this ends up being the integral from 0 to infinity of x times, it was lambda times e to the minus lambda of x dx. So there's the PDF over this region, otherwise it's 0. And we're multiplying by x. And the way to handle this is called integration by parts. So I'm going to write this down real quick. So the integration by parts is if you're integrating u dv. So here's one function, here's its derivative. That's the same thing as u times v minus the integral of v du. It's integration by parts. And really what this is an anti-product rule. All right, so what we're going to do here to put ourselves in this position, we're going to have two variables, u and v, two functions. So here we're going to let this function. Well, first of all, let's say this is the limit as t goes to infinity, an interval from 0 to t, because in proper interval, of x times lambda e to the minus lambda x dx. What am I going to do? I'm going to let u be equal to x. So in integration by parts, we let u often be something that when we differentiate it, it is eliminated or decreased. So du will be equal to dx. dv, the other part of the is e to the minus lambda x, and I need a lambda here. Its integral, so if you integrate this, you're going to get is equal to minus e to the minus lambda x. Let me make sure that I indicate what I did there. This is the integral of lambda e to the minus lambda x. And we worked with that a few seconds ago, and that's minus e to the minus lambda x. You can find that out through new substitution. So, okay, what we get, the expected value of x is going to be equal to the limit as t goes to infinity. And here, this integral is going to be uv. So here it's u. U was x. V we found to be minus e to the minus lambda x. We need to evaluate that from 0 to infinity. Minus the integral of v du. That's going to be, v was minus e to the minus lambda x. Du was just dx. Now this is equal to, this should have been t. This should be from 0 to t. This is equal to the limit as t goes to infinity of t is minus t, e to the minus lambda t. And then when I stick it 0, I have to subtract it. So this minus becomes plus. So it's 0 times e to the minus lambda 0. And then this 2 minus is, well, I'll leave that minus here. This is a minus. Here, the integral of e to the minus lambda x, minus e to the minus lambda x, that is going to be equal to, so this is, I need to use substitution here. If you want, you can let w be equal to minus lambda x, then dw is equal to, it would be minus lambda. And so, here, this would be the integral from, I'll write down x runs from 0 to t. And here, what we have is, I need a lambda. And so what I'm going to write is I'm going to write down e to the minus lambda x. And here, I'm going to put minus lambda. This should have been dx. And what I've done is I've stuck in this lambda, which is a constant, and I can do that as long as I compensate, with it being a constant, compensate for that insertion of multiplication by a lambda by dividing by lambda out front. I can take that lambda that's in the bottom outside the interval because it's a constant. Now, here, this is equal to the limit as t goes to infinity. Well, this part is minus t e to the minus lambda t. And then here, this will be minus 1 over lambda. The integral e to the something, derivative of the something, it's just e to something. So here's the e to the minus lambda x, evaluated from 0 to t. So this ends up being the limit as t goes to infinity of minus t over e to the minus lambda t, be plus lambda t. And then here I have minus 1 over lambda. When I stick a t, it could be e to the minus lambda t. And then when I stick a 0, don't forget I have to subtract what I would get when I stick in 0. And it's already got a minus in front of it, so that makes it a plus 1 over lambda e to the, here, when I stick in 0, I just get e to the 0. Okay. Now it turns out, as t goes to infinity, what you're going to end up getting is infinity over infinity. You use L'Hopital rule, take the derivative of the top, that's going to be minus 1. The derivative of the bottom is going to be lambda e to the lambda t. But as t goes to infinity, this is going to go to infinity. And you're going to have minus 1 over something huge. That goes to 0. So what we end up getting here is 0. This part also goes to 0. Let me take that limit. And this guy's a constant, which is 1 over lambda. And that's just equal to 1 over lambda. And that's what the expected value is. So that ends that proof. Well, let's look at its variance. Fact, if x is exponential with parameter lambda, then the variance of x equals, I think I have it. 1 over lambda squared. Let's do the proof. Okay, so let's note, we know we're talking about exponential random variable. Note the variance of x by our formula is equal to the expected value of x squared minus the expected value of x to b squared. Well, this guy I've already got. So, what is the expected value of x squared? Well, it's going to be equal to the integral from minus infinity to infinity of x squared times f of x dx, which in this case is equal to the integral from 0 to infinity of x squared times lambda times e to the minus lambda x dx. And to handle this integral, to get an antiderivative, we're going to have to use integration by parts twice. So I'm going to let u be equal to x squared du will be equal to 2x, dv will be equal to lambda, that's lambda, e to the minus lambda x. And from our previous experience, we know that that antiderivative for this guy, the integral of this guy, is e to the minus lambda x. And so this is equal to the limit as t goes to infinity of 0 to t, an integral from 0 to t. Here this is going to be x squared lambda e to the minus lambda x dx. And now I'm going to use the integration by parts. Work if we've listed. And tell you that that's equal to the limit as t goes to infinity. And here this is going to be uv, so it's going to be x squared times e minus e to the minus lambda x. We're going to evaluate that from 0 to t. And then minus the integral of v, which was minus e to the minus lambda x du. Du is 2x, well I should have said dx. That's what we have. And this is from 0 to t. Okay, this is equal to the limit as t goes to infinity. Here, when I stick in t, I have t squared minus t squared over e to the lambda, that's lambda, t. When I stick in 0, well, we just get 0. So, but it's minus and minus 0, so I'll just say minus 0. Minus, here, I have to use integration by parts again. I'm going to let u be equal to 2x, du will be equal to 2dx, dv is equal to minus e to the minus lambda x. V, in this case, now I need this lambda here, so what I get is 1 over lambda e to the minus lambda x. That's what I get. So if you will, let's make this a little lower. It's minus uv, so I'd write down 2x times 1 over lambda e to the minus lambda x minus the integral of v du, so it's the integral from 0 to t. Remember, this has got to be evaluated from 0 to t. Minus the integral from 0 to t of v, which is 1 over lambda e to the minus lambda x, du is 2 dx. This is equal to the limit as t goes to infinity minus t squared over e to the lambda t minus the quantity. Well, let's help here. When I stick in t, I'd have 2t over lambda. Here this will be an e to the minus lambda t. And when I stuck in 0, we get a plus 0. So it'll be minus and minus, it'll be 0. But this part's 0. 0 times this will be 1 over lambda is 0. And then a minus makes a plus. Here, to integrate this, this is almost e. So I made this a plus because these two minuses make a plus. To integrate this, I'm going to go through this kind of quickly. It's a u substitution problem. We got e to the something. The way that we integrate e to the something is that we need the derivative of something. The derivative is minus lambda. So I stick that there and then compensate for it outside. The 2 over lambda c. The compensation will be times a minus 1 over lambda. And then the integral of this is e to the minus lambda x, and I have to evaluate that from 0 to 2. This is equal to the limit as t goes to infinity. This is minus t squared over e to the lambda t. This is minus 2t lambda e to the minus lambda. No, it's just plus. This would be plus. I made a mistake. I make that plus. E to the lambda t. Here, when I stick in t, it would be minus 2 over lambda squared. When I stuck in t, I would have e to the minus lambda t, and then this is creating a minus, but then you subtract from it, which you get when you get 0, so it becomes a plus. Here's 2 over lambda squared. When I let x be 0, this is minus lambda times 0. That's 0. It's e to the 0. That's just 1. Now, it turns out that this here, if you take the limit t goes to infinity, you use L'Hopital's rule twice. This goes to infinity, this goes to infinity. But what you find out is this goes to 0. The same thing happens here. You use L'Hopital's rule once and you get 0. This guy, when you let t go to infinity, this guy goes to 0, so this whole thing goes to 0. And then here it's 2 over lambda squared. So what we found is the expected value of x squared is equal to 2 over lambda squared. That's what we are. Okay. So the variance of x is equal to the expected value, remember, of x squared minus the expected value of x to b squared. We've already found this. This we just found. This was 2 over lambda squared, and that's what we wrote. And then this is minus 1 over lambda to b squared. And so that ends up being 1 over lambda squared. That's overlap squared. So that's what we get. And that's what we said we'd get. So that's the inverse proof. Next thing I want to look at is something called the gamma random variable. So definition, it's going to be a little bit lengthy definition. A random variable x is called a gamma random variable if its PDF is, okay, so is its f of x is equal to, see if I can remember without looking. So let's see, I think it's lambda e, I need to look. So it's lambda e to the minus lambda x to the alpha minus 1 over something called gamma of alpha. So I've got to find gamma of alpha. When here x is greater than or equal to 0, and it's 0 otherwise. So that's its PDF. And I need to write down things about the specific quantities involved, lambda, alpha, and what was gamma alpha. So, where lambda is greater than 0, alpha is greater than 0, and gamma of alpha is defined to be the interval from 0 to, from 0 to infinity, of e to the minus x to the alpha minus 1 dx. And before we go on to do things about a gamma random variable, let's first work about this gamma function. Gamma of alpha is known as gamma function. The first thing is I'm going to list a fact and then leave it to you to prove. Okay? So here's a fact. And it'll be in the next homework assignment. It says that if n is a natural number, then gamma of n is equal to n minus 1 factorial. Prove, let me write this down here. N minus 1 factorial. Here's another fact I'll prove. Is that gamma of alpha is equal to alpha minus 1 times gamma of alpha. Okay, so I'll prove this. So before I go to this is left to students at previous classes. So you can go ahead and work on it. Now, the proof is that if we look at gamma of alpha, that's equal to the integral, it was from 0 to infinity, e to the minus x, x to the alpha minus 1 dx. Okay. Wait a second. I didn't write down. Exactly right. I'm sorry. I miswrote this fact. Let me go back. I miswrote this fact. We have to change this. So here is alpha minus 1. All right. So we're proving it over here. So gamma alpha is equal to this. Okay. Well, let's use integration by parts. Let's let u equal to I need to say, let's let u equal to e to the minus x. See what happens. If it doesn't work out, we'll keep working. du is equal to e to the minus x, minus sign of phi. Yeah, I like that. Let's let, either way, won't happen. Let's try that. Let's let u equal e to the minus x. So, wait a minute, just a second. So, du is equal to minus e to the minus x. dv, let's let it be equal to, yeah, this number. Let's try this first. Okay. Let's see what happens. Let's let u be equal to x to the alpha minus 1. Then du is alpha minus 1, x to the alpha minus 2. Yeah, this looks better. dv is equal to e to the minus x. v, which is the integral of this, is going to be equal to minus e to the minus x. So by integration by parts, we have gamma of alpha is equal to, let's rewrite this. The limit as t goes to infinity of 0 to t e to the minus x, x to the alpha minus 1 dx. And then by integration by parts, this is equal to the limit as t goes to infinity. Here, this is going to be, it's going to be u v, so it's going to be minus e to the minus x, x to the alpha minus 1, evaluated from 0 to t, and then we're going to have minus the integral of v, which is minus e to the minus x, du, which is alpha minus 1, x to the alpha minus 2, dx. That's where we should have dx. Okay, everything's fine. That's the way it works. Now, here, I didn't write this in the fact, but we're going to assume that alpha is bigger than 1. Okay? Alpha is 1 or bigger. Okay, that's what we're okay, so alpha is bigger than 1. And so here, we keep working. This is equal to the limit as t goes to infinity. This will be minus e to the minus t, t to the alpha minus 1, minus, which makes it a plus, and here this will be e to the minus 0, so that's just 0, and then it would be 0 to the alpha minus 1. And then this is minus A minus makes a plus. This is the integral, and I made a mistake here in my notation. Let's go back. So right here on this last line, I should have had from 0 to t to this integral balance. Okay, so put that back in. Okay. So here's plus the integral from 0 to t of e, because the two minuses make plus, to the minus x, and I can pull out the alpha minus 1, out in front it's a constant, x to the alpha minus 2 dx. Now here, this is t goes to infinity, can be shown to be 0. This is 0, so we end up getting the limit as t goes to infinity of alpha minus 1, integral from 0 to t, of e to the minus x, x to the alpha minus 2 dx. But that's just equal to, symbolically we can rewrite this as alpha minus 1 times, instead of saying this dummy variable with the limit, we would just say since the proper integral from 0 to infinity of e to the minus x, x to the alpha minus 2 dx. And that's alpha minus 1. If you look back at the definition of gamma of something, it's the integral from 0 to infinity of e to the minus x, x to 1 minus, to the something minus 1. Okay? So if you have gamma of alpha, it's alpha minus 1. But here we have x to the alpha minus 2. That's nothing more than gamma of alpha minus 1. And that's what we were trying to show. Okay. So that proves that fact. And now we're going to turn to facts about the gamma random variable. And so the first thing we're going to do is we're going to know that the integral from from minus infinity to infinity of f of x, where dx, where f of x is the PDF of the gamma random variable. This is going to be equal to, well, remember that's defined to be 0 when x is non-zero. And so here, we have from 0 to infinity. So I'm going to write this down. I want to make sure that I wrote down the right thing for you. This was lambda e to the minus lambda x to the alpha minus 1, and all over gamma of alpha when x was greater than or equal to 0 and 0 otherwise. And so that's why we can break this integral into an integral just from 0 to infinity, the part where x is positive, of lambda e to the minus lambda x to the alpha minus 1 over gamma of alpha. All right, you can pull out that gamma of alpha outside. So that's equal to 1 over gamma of alpha and I'll pull out well, it's integral from 0 to infinity of lambda e to the minus lambda x, and then it's lambda x to the alpha minus 1 here. And that looks a lot like the gamma function, okay? It's not perfect. So what we're going to do to make it work is we're going to do u substitution. Let u be equal to lambda times x. And the derivative of u will be just lambda dx. So this lambda dx, 1 over gamma alpha is what we have, integral from 0 to infinity. This lambda dx is du. This is e to the minus u. That lambda x is u, so it's u to the alpha minus 1. Here's the du. Now that is that is nothing more than gamma of alpha. And so these two quantities cancel each other just to leave a 1, and that's what we expect. All right, let's move on to the expected value of the gamma random variable. So as a fact, the expected value, if x is a gamma random variable, with parameters alpha and lambda, then the expected value of x is equal to alpha over lambda. We'll prove that. So to prove, here, remember the expected value of x will be the integral from minus infinity to infinity of x, f of x dx. But that's going to be equal to the integral from 0 to infinity, because of the way f of x is defined, of x. This is going to be lambda e to the minus lambda x, lambda times x raised to alpha minus 1 over gamma of alpha dx. So that's equal to, well, let's pull out that 1 over gamma of alpha. And here, look at this as being the integral from 0 to infinity. And then I'll rewrite this as e to the minus lambda x. And I'll take this lambda x and put it inside here. And this will be lambda x to the alpha. And that's all we'll have, dx. Okay. Now, that's very close to what I need. But what I'm going to do to be like what we had when we showed that the integral of the PDF is equal to 1, what I'm going to do is have 1 over gamma of alpha, and then I'm going to multiply that by a lambda in the bottom. Integral from 0 to infinity. I put a lambda here as a constant. This lambda here and this lambda here will cancel. E to the minus lambda x to the alpha dx. What we're going to do, like we did before, is we're going to let u be equal to lambda x, du then will be equal to lambda dx. So we end up getting 1 over lambda gamma of alpha times, this is the integral from 0 to infinity. Here this would be e to the minus u, because that's what lambda x is, u to the alpha, and lambda dx was nothing more than du. Okay? All right, that's what we are. And one thing that this right here are for the x values, but if you look here, with lambda being positive, if x started at 0 right here, then u is going to start at 0. This is really for u value. And if x gets really, really huge, then as x gets really, really huge and you multiply by lambda, that still gets really, really huge, and so u will go to infinity. So these limits of integration are for u as well. Okay, so what we have then is the expected value of x. Look where we are. It's 1 over lambda times gamma of alpha. And if you look at that second integral, that's nothing more than a gamma. It's a gamma of alpha plus 1. But by the fact that I proved to you this is equal to 1 over lambda gamma of alpha. Here, this will be alpha, okay, so 1 less than what we're taking gamma of, and then gamma of alpha. And these two gammas of alphas will cancel, and that's equal to alpha over lambda. That's what we want to show. Okay, fine. As a fact, if x is a gamma random variable with parameters lambda and alpha, then the variance of x is equal to alpha over lambda squared. We're going to prove it. We'll do this, and that'll be the last thing we do today. Okay, so here's the proof. We note, or recall, the variance of x is the expected value of x squared by minus the expected value of x e squared. We found this with alpha over lambda, so it's going to be alpha squared over lambda squared for that part. Note, the thing we don't know is the expected value of x squared. What's it equal to? It's going to be equal to the integral of x squared from minus infinity to infinity, f of x dx, which we can rewrite as the integral from 0 to infinity of x squared, because of the way the PDF is defined, lambda e to the minus lambda x to alpha minus 1 over gamma of alpha. We pull out that 1 over gamma of alpha. Here, we pull out a lambda. I'll put in another lambda. Is integral from 0 to infinity, x squared, lambda squared. It was lambda, but it's lambda squared now. E to the minus lambda x to the alpha minus 1. That's it. No, I pulled out the gamma of alpha. And so this is equal to 1 over gamma of alpha times lambda. Here we take this x squared and this lambda squared, and we put it in here, and we get integral from 0 to infinity, e to the minus lambda x to the, well, I'd be adding 2 of the lambda x's. So it'd be alpha plus 1 here, dx. This is 1 over lambda times gamma of alpha. And to use our trick that we have been using, I'm going to let u be equal to lambda x, but I need a lambda here. So let's put another lambda in the bottom, making lambda squared. 0 to infinity, lambda e to the minus lambda x to the alpha plus 1 dx. Okay? So this lambda here, we cancel out one of these lambdas here, and you see you have the exact same line. Why do I need this lambda here? Again, we're going to let u be equal to lambda x. Du is equal to lambda dx. And so this part is equal to 1 over lambda squared gamma of alpha. Here, this is integral from 0 to infinity. Now, this is in terms of u. This is e to the minus u. This is u to the alpha plus 1. And this lambda dx is du. That's equal to 1 over lambda squared gamma of alpha, and here, this is gamma of alpha plus 2. We're about finished. This is equal to 1 over lambda squared gamma of alpha. What's alpha plus 2? It's alpha plus 1 times gamma of alpha plus 1, which is the same thing as 1 over lambda squared gamma of alpha. Here I have alpha plus 1, but now what's gamma of alpha plus 1? It's alpha times gamma of alpha. So we end up getting, here we have alpha squared plus alpha over lambda squared. These gammas of alphas will cancel. That is the variance, that's the expected value of x squared. So the variance of x is equal to alpha squared plus alpha over lambda squared minus the expected value of x. Remember, that's alpha squared over lambda squared. And so we just end up getting alpha over lambda squared. That's what we want to get. Okay. Well, that's enough for this video lecture. I didn't get to the normal random variable at all, but that's what we'll start with next time. Thank you very much for your time and patience.